Through solution and topochemical. Topochemical is things start forming on the surface. Through solution is things dissolve on the surface and crystallize. So same idea but different ways of doing it. Through solution is what I talked about so far. Anhydrous compounds become ions, hydrates form. Topochemical reaction happens directly on the surface. First one is more common, second one not that common in cements. Structure formation, pozzolanic reaction. All of you know about pozzolanic reaction, right? Calcium hydroxide is created as a result of cement hydration. Calcium hydroxide is not very good because it is soluble in water. You need something to eat up that calcium hydroxide. Pozzolanic materials like fly ash are good at doing that because they have silica or alumina that will react with calcium hydroxide to form CSH, further CSH, or sometimes mostly CASH gels, calcium aluminosilicate gels, which will form, fill the space better. Your porosity is controlled. So fly ash is actually a good thing. Now, when does fly ash become bad? Is there a situation that you can think where fly ash is not very useful? Coarse are fly ash because they don't react well. Yeah. Why beyond certain limit?
Because it doesn't react much.
So you won't get CSH. Right. So if you don't have enough fly ash, if you don't have enough calcium hydroxide, do you know how much calcium hydroxide roughly as a percentage of the total volume that will require no more fly ash to be added? Depends on silica and alumina content of fly ash, right? So if you have, now fly ash also reacts starting from the surface. So have you done, if any of you have done this research, have you done a 30% fly ash or a 40% fly ash, and at 90 days have you gotten a system with no calcium hydroxide remaining? Then why are we very worried about the amount of fly ash that you can go in? You will get, after 90, say assume that fly ash will take time to react. 90 days. Do a TGA, thermogravimetric analysis of your cement paste after 90 days. You will still get calcium hydroxide there. You can't eat up the entire calcium hydroxide with fly ash. Fly ash, calcium hydroxide also keeps producing. See, I know there's no whiteboard. Okay. So think about a cement particle. So this is competition for reaction. Think about a cement particle, think about a fly ash particle, okay? This cement particle reacted from the surface, like we were talking about, formed CSH and calcium hydroxide. This fly ash ate up the calcium hydroxide, reacted, formed CSH, right? But there is still residual solution. That solution diffuses through the initial cement particle, goes a little more in, produces more CSH, and then more CH also comes in. Some other fly ash does it. So until the cement gets hydrated completely, your calcium hydroxide is not going to go away. Unless, there's one caveat to that rule, unless you dump a lorry load of silica fume. Silica fume will eat up calcium hydroxide very quickly because silica fume is telling, I'm really fine. I don't need anything else. I'm this reactive silica. You show me calcium hydroxide, I'll immediately react with it. I don't need an external medium for me to help you. See that? So if you have a lot of silica fume, you can deplete calcium hydroxide. Depleting calcium hydroxide with fly ash is a researcher's dream. It's an utopian dream. You will have calcium hydroxide in a system with fly ash. So when people say, oh, when you have fly ash, the pH of the concrete goes down because my calcium hydroxide is low, therefore it will corrode. Nonsense. Okay, your pH will go down. Yes, your pH of your concrete will go down. pH will go down from what to what? I'm not going to take the pH down from 12.6 to 9. I'm going to take the pH down from 12.6 to 11.6. But more importantly, you have got a lot of space filled that you won't have ingress of ions into the concrete anymore. Why are you worried about the pH? You see the argument? And then if your steel is sitting there just relying on the pH that the concrete provides, good luck. And how many of you have seen steel that is put in any concrete that is not rusted? When you what's the color of steel when you put in concrete? You see any local construction? Brown, right? Unless you coat the steel with epoxy, yeah, then you have an argument. Or I'm saying, oh, I have galvanized steel, I want to protect my galvanized. Yes, you have a point. But anytime we do here, you have corroded 15% of the surface area of steel, and then, even then, the whole thing stands up pretty well, and then you're complaining about, oh, calcium hydroxide is a problem now. I need to kill all of that. You don't have to. That's over-engineering for a simple system like concrete. Don't try to kill all the calcium hydroxide. Whatever is there, let it stay. Use fly ash as a source to do secondary reaction and some space filling. Now, fly ash has a lower density than cement, right? What's the density of specific gravity of cement? 3.15. General fly ash has specific gravity? 2.4, 2.5, which means if I replace 15% of cement by fly ash, I am putting in more volume of fly ash, right? 15% by mass will end up to be 20% by volume, which means even if it doesn't react, forget it, your space is being filled. Just consider this as a cheap filler, non-reactive filler. I'll talk to you about the effect of fillers and filler effect and what they do in these systems. It's very important to understand that you don't have everything else to react. You don't have everything to react. You don't have to react the whole thing. Fillers are good, and fillers will actually do some good things. So fly ash can remain as filler. So the concern should not be, oh my God, fly ash will not react after a certain point. The concern should be, is my fly ash too coarse to be put in the system? Is the carbon content of fly ash too high to cause problems like rising of carbon to the surface, interacting with other chemical admixtures? Is my fly ash having too much of residual carbon? Is my fly ash high in alkalis? Those are the questions to ask rather than blanket saying, I will allow only 30% fly ash. So if you do performance specifications, check the fly ash. My total alkali content of my cementitious material should not be greater than so and so. How much fly ash will be acceptable for that? Now, I don't know, do you have alkali silica reaction in India? Do you have? There is actually in northern parts. So I have, I was called once for some consulting work in Uttar Pradesh, or Uttarakhand now, Uttar Pradesh formerly. And they have quite a bit of reactive aggregates because Himalayan fault, again, reactive aggregates are because of how the geology is formed. From the Himalayan fault, there was a few places where there was faulting of rock layers through which you're getting a lot of aggregates, exposed cherts and stuff in that aggregates. So if you have ASR, in the US, plenty of ASR. United States being a newer continent than India, things haven't stabilized to the level that Indian subcontinent and the Eurasian plate has. So you have much more of reactive aggregates there, and so fly ash becomes a very, very useful thing to control alkali silica reaction, provided your alkali content in fly ash is low. So that's a question to ask. How much is my alkalis in fly ash? How much is the free carbon in fly ash? What's the particle size of fly ash? If you answer those questions, then you can design a concrete mixture and do trial testing in the lab to satisfy all the performance requirements. We have done, I have done, one of my students recently did a work with 85% fly ash and 15% OPC for a 50 megapascal concrete. 90 days, 50 megapascal, 85% fly ash, class F. Possible. Yeah, we had to cheat the system somewhere, and I'll tell you about cheating the hydration system. You have to cheat the system, and you have to make the cement think it is something else, right? This is performance boosting. You tell somebody you're really good, you're really good, you're really good, it becomes good, right? You can run fast, you can run fast, you can run fast, and suddenly you see people running fast. So you cheat the cement by doping it with something and telling it that, you know what, you're not just the ordinary Portland cement. Here is a little bit of performance enhancing drug for you, and that'll do really well. So,
acceptable size of fly ash particle?
there are different ranges. The rule of thumb is that fly ash particles should be of the size of cement particles, in that range, so that your cumulative particle size distribution is not significantly different. That is purely from the point of view that you will get the filling of particles in a volume fairly nicely. The advantage also is that with fly ash, if you have class of fly ash, and if the fly ash is really spherical, you can reduce the amount of water. Therefore, the effective particle packing will even be better. Now, there are companies that actually do what's called the ultra-fine fly ash. When the fly ash comes out through these separators, the cyclonic separators, they have two different separators. One is for the really fine ones that go up, typically 3 microns and lower. And in the US, such fly ashes, which are 3 microns and lower, are sold almost at the price of silica fume, because they effectively do what silica fume does without the side effects of silica fume. The side effects of silica fume typically being very high early strengths and cracking associated with that and shrinkage. That'll avoid all of that. So 3 micron and lower, it's called ultrafine fly ash. That sells for almost the price of silica fume. More expensive than cement. Okay. So a unit volume of cement hydrates to double its volume, right? If I take 1 cubic centimeter of cement, you will get about 2.15 cubic centimeter of the reaction products. I probably will show you some calculations in the next class. Proof is elaborate and complicated, so I'll skip that, but I'll show you some examples. Actual number is 2.1, 2.15. Volume changes as a result of hydration. Shrinkage, all of you are comfortable with the idea of shrinkage. Different types of shrinkage, right? There is drying shrinkage, which happens late. There is chemical shrinkage, that's what we're talking about, because of the change in volume of the reactants and the products. There is autogenous shrinkage or self-desiccation, where cement needs water to react, but this cement grain is starving from water, whereas the adjacent cement grain already reacted and has a reaction product that contains water. Therefore, this non-reacted cement will draw water from the hydrated products. Therefore, the hydrated product will have to shrink. Autogenous, self-desiccation. So all these things happen, and all of these have implications in how the microstructure forms and the durability. Exothermic reaction, all of you know that. Portland cement is exothermic. Heat is generated. C3A and C3S are chiefly responsible. This picture, all of you have seen this? All very familiar. Initial dissolution heat. Heat goes down. You have a plateau where CH nucleates. This plateau helps ready mix manufacturers to carry the concrete around to wherever they want without further reactions. You can add chemical admixtures to extend this plateau. You can add retarders to extend this plateau. You can add accelerators to shorten this plateau. Then you have growth of CSH and CH in the acceleration state. And then the maximum heat release is done. And then it comes down. And then you get a steady state where the entire process is diffusion control, which means you still have cement left to hydrate. You still have water in the system here and there. But then the process is diffusion control. Again, remember your basic physics. Transport of water or moisture can happen through absorption, adsorption, diffusion, wicking, lot of different phenomena, right? Absorption is taking water inside. Adsorption is tying water on the surface. Diffusion is a slow transport of water. Wicking is through a pressure gradient. Okay? All of these mechanisms happen within a cement paste. If you actually look through different hydrating cement paste with boundaries, you can see even pressure differences, osmosis. Even osmosis happens inside the systems. All of you know osmosis, right? Through a membrane potential, concentration gradient. All of these happen within these systems. Okay, so rapid heat evolution, first 15 minutes roughly. Dormant phase, 2 to 4 hours for transportation. Acceleration stage, 4 to 8 hours for initial settings happen somewhere here. Final setting happens somewhere here. Deceleration, and then a steady state, which is diffusion control. Stuff that we have talked about, I think you should figure it out. How do you find out the heat of hydration? I'm only halfway through my number of slides, my God. Okay. Isothermal calorimetry is what is used to determine heat of hydration. This is what I talked about, simple thermodynamics ideas. Rate of heat production. Think of your cement hydration as an internal combustion engine. Produce heat, use up the heat, throw away the remaining heat, right? Produces heat. Again, instead of mechanical energy, you are producing chemical energy. Heat through a chemical reaction. So rate of change of heat with respect to time is equal to rate of heat exchange plus rate of heat accumulation. So if I have a box of concrete that I'm casting now, the cement that's hydrating is producing heat. Some of the heat is accumulated within, some of the heat is dispersed out, right? If I actually measure the amount of heat that's exchanged to the outside, and I tell the outside whatever heat is coming in, I will either take off heat or give heat to keep that temperature at a constant value. Can I then know how much heat is exactly coming out? Right? So I have a system from which heat is coming out. I say for example, X amount of heat is coming out. I am measuring that amount of heat and telling, okay, this X amount of heat gets me only 18 degrees Celsius. I will supply external heat to make it 25. Or this heat is actually giving me 27. I'll take off equivalent 2 degrees Celsius and make it 25. So if I keep it ambient, air conditioner principle, if I keep the room ambient at 25, will I not know if the sun is beating outside at 35 and I have a certain insulation characteristics for my wall, will I not know how much heat came in and the air conditioner heat exchanger has to control so that the room temperature is maintained at 25? Same idea. That tells you how much cement has reacted. So heat of hydration is a good way to tell you how much of cement has reacted, and finally you convert it into a term called degree of hydration. Right? You use a term called degree of hydration, which is effectively a parameter from heat of hydration to tell you how much of cement is hydrated. Now, this again is an important determinant of the microstructure. When you have heat that forms in the structure, when you have heat that is being released, two things happen like in any heat transfer process. First, your cement hydrates, you cause heat. That heat, again, like I said, everything wants to be in a state of equilibrium. That heat would try to equilibrate the system with whatever is the ambient, right? Get that? That will be the equilibration part of the heat. And also, this heat, anytime you give heat, what will happen to the chemical reaction? Anytime you increase your gas burner heat, your food will cook faster. Your reaction will happen faster. Two different competing things. The heat is trying to increase the rate of reaction, but the system is trying to come back to an equilibrium. Which process wins in which part of your concrete determines how the microstructure of that part is going to be. Therefore, if I have a mass concrete, my microstructure, you bring the same concrete from the same truck, the microstructure on the outside of the mass concrete and inside of the mass concrete are never going to be the same, because this competition is never one-sided. It keeps going back and forth. So now that leads us to what I'm going to talk about tomorrow. You can never expect one microstructural characterization or one microstructural determination to tell you the story of what's inside. Okay? Generally, you can define what is being formed. Generally, you can get an idea of how things are forming, but as in any investigation, the location of where you're sampling from becomes extremely critical. So you have a problem with a concrete. Somebody tells you investigate what it is. You take from one place, you make a conclusion. You're more often going to be wrong than right, because you're seeing only a part of a story in one part of the structure, right? Because heat of hydration directly influences how much heat is exchanged as to how much heat is used to equilibrate the process, results in different microstructures in different locations. Okay. Okay. Few why is heat of hydration important? You probably have seen all of these. Member thickness and heat. Thicker members, more heat. Thinner members, more dissipation, faster dissipation, so lesser heat. Heat of hydration with different limestone contents. You can basically see here, that's pure OPC. And then if I take 0.7 micron limestone, really, really fine limestone, okay? Cement particle median size about 15 to 20 microns. 0.7 micron limestone is really, really fine limestone. If I put in really fine limestone and replace 10% of cement with limestone, and this limestone is not reacting, but look at the hydration heat. What is it doing? I have dropped 10% of the cement, but the limestone is not reacting, but the limestone, because it is extremely fine, acts as what is called nucleation agents. We'll talk about nucleation and growth tomorrow because, again, microstructure depends on nucleation. So you basically have these very small particles around which calcium hydroxide is very famous for this. Calcium hydroxide wants something to lean on, wants something to precipitate. It is not going to precipitate. Just you put in a solution of calcium hydroxide and try to supersaturate, it will not precipitate. It wants a surface on which it can precipitate. Okay? So it is called heterogeneous nucleation. It needs a surface to precipitate on, and therefore, when you have a cement grain as a surface, when you have a fine limestone particle as a surface, calcium hydroxide starts to precipitate on the surface. When calcium hydroxide precipitates on the surface, which means in the solution, now calcium hydroxide is undersaturated, right? Because it got precipitated. More reaction will happen from the cement, more calcium hydroxide and CSH will form, therefore your heat will be more even if you have, look at all these cases. When I get to a 15 micron limestone, what happens? Look at this. When I make the limestone 15 micron, what is the importance of 15 micron? Roughly the same size as cement. What's happening to it? Whether I put in 10%, 20%, is there any change in the total heat of hydration? Why? This is what I call cheating the system. Okay? This is how you cheated the system by putting in limestone. So effectively, if you are worried about sustainability, I don't want to use so much of cement, fair enough. Take off 10% of cement, take off 20% of cement, take off 20% of cement here with a 15 micron limestone. Have I compensated anything in terms of heat? Have I compromised anything in terms of heat? No. I've gotten exactly the same system back. Right? Whereas if I want more heat of hydration, if I have a cold weather concreting, I can use this technique with reduction in cement. So basically my argument here is, don't have to increase cement content just because it is cold. You see this all the time. Oh, cement content has to be increased to 550 kilograms per meter cube because temperature is going to be 16 degrees Celsius. You don't have to. You do not have to do it. You can tweak the system slightly, still be sustainable, still reduce the amount of cement. And this is what is called performance by design. Not randomly putting the material, understanding what the system does, and therefore now I can tune my system and say, don't worry, I can still do 350 kilograms per meter cube of cement, I can still get you the concrete, all I need to is to add 5% of limestone, 10% of limestone, or 5% of any filler. That is a technology that you want to come in. Now, that technology is very hard to come as long as prescriptive specifications are there, right? Why would a cement manufacturer be so gracious as to reduce the cement content in a concrete of a ready-mix plant that he owns? I've been in both places, I know that. I've been told by Grasim when I was working, get our cement content to at least 450 while I was fighting for 350. I was told we want this concrete to have 450 kilograms per meter cube. I said I can get it at 350. Doesn't matter our cement. We need to sell cement. Right? So why would, if you have, as long as you have prescriptive specifications, this will not happen. That's the idea of getting into performance-related specifications. Now you can decide, okay, I can tweak the system. in all these different ways. And that's where the policy of how you specify and sell concrete and what is actually happening at the scientific level, they start to merge. In many countries, including India, and most of the time in the US, they're handled by completely different people. You see that? The guys who make the decision, the economic decisions, typically are driven only by economics, not by the science and engineering. Right? That's why we need, again, it's a fact. That's why you need more of technocrats than bureaucrats. So that you now know, if you see it in front of you and you have a bid and you are looking at costing, you can compare it because you know the system and say, I want this because this is giving me a sustainable material at a lower cost, and because of these characteristics, it'll give me the performance. You see that? You see how these things are so disconnected in real world. And unless somebody gets this performance-based specifications and the ready-mix plant says, okay, you need 40 megapascal concrete, you need this amount of heat, right? I can give you with this. And then they'll make it cheaper, they'll make more business, they'll make more money, their shareholders will be happy because they're making more money. That's how economy should move. So there is a very good link between technology and economy, which software industry has wonderfully capitalized if you look at it. I mean, look at your cell phones, right? Have any cell phone company have you asked a cell phone manufacturer, Samsung or Apple, have you told them, I want this feature in your phone? No. They give it to you, preempting you, knowing what you want, right? That is why you are willing to pay a premium for a Samsung 9 when it comes out, or an iPhone 10 when it comes out. You are willing to give a premium because you know they have anticipated your needs. We never anticipated the customer's need in our industry. We just did what is called the least path of least resistance. We want this much to satisfy, we'll just give what they have to satisfy. When they have a more demand, then you're not satisfying. Now you have WhatsApp, you have IMO, you have all these different things in your phone, you get it fully loaded with all these, and you have it, I don't even know how to use, that's what you say, right? I don't know how to use this phone. It takes you 2 years to figure out how to use that phone, and then they come out with a new version with even more add-ons. We never hooked up the customer. In our business, we lack